And now in this lecture I'll answer two questions. In the first question we find out the area of this trapezoid ABCD, and in the second question we find out the area of this quadrilateral ABCD using two different methods. So let's start with the first question. In the drawing we have trapezoid ABCD. Side AD equals to 41 units in its length. Side CB also equals to 41 units in its length. Side AB equals to 50 units. Again, our task is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Okay, again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to side AB, and therefore quadrilateral ABCD is defined as a trapezoid. If we define the length of side DC as A and the length of side AB as B, then this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the right edge over 2. The right edge was created like this with the two parallel bases. Okay, again, the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is to say A plus B, times the right edge over 2. So first of all, we define relevant points to this question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent CB with this circle. This point is point F. Likewise, we define the point of tendency of tangent DA with this circle. This point is point G. And finally, we define the point of tendency of tangent AB with this circle. This point is point H. So here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. We focus on this common standpoint, point D. From this common standpoint, point D, we have two tangents to this circle, tangent DG and tangent DE. And according to rule 2, they are equal to each other. That is to say, DE equals to DG. So if we define the length of tangent DE as A, that is to say, tangent DE equals to A units in its length according to our definition, then the length of tangent DG must be also equal to A because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint, point A. From this common standpoint, point A, we have two tangents to this circle, tangent AG and tangent AH. According to rule 2, they are equal to each other. That is to say, AG equals to AH. So if we define the length of tangent AG as B, then the length of tangent AH must be also equal to B because they are equal to each other according to rule 2. We focus on this common standpoint, point C. For this common standpoint, point C, we have two tangents to this circle. Tangent DE and tangent CE and tangent CF. And according to Urdu, they are equal to each other. That is to say, CE equals to CF. So if we define the left from tangent CE as C, then the left of tangent CF must be also equal to 3 units. So they are equal to each other. And finally, we focus on this common standpoint, point B. From this common standpoint, point B, we have two tangents to this circle. Tangent BH and tangent BF. And according to Urdu, they are equal to each other. That is to say, BH equals to BF. So if we define the left of tangent BH as D, then the left of tangent BF must be also equal to D because they are equal to each other. What is the value of side DE plus the opposite side CB? DE plus CB, DA, side DA, plus the opposite side, side CB. DA plus CB in total will be equal to A plus B plus C plus D. See again. DA plus CB equals to A plus B plus C plus D. Likewise, what is the value of DC plus the opposite side AB? Side DC plus the opposite side AB in total equals to A plus B plus C plus D. So if we found out that side DC plus the opposite side AB also equals to A plus B plus C plus D. And because of the fact that those two expressions, they are both equal to A plus B plus C plus D, they must be equal to each other. That is to say, DA plus CB equals to DC plus AB. So, you know, DA plus CB equals to DC plus AB. DA equals to 41 units in its length according to what is given as the question. Plus CB. CB also equals to 41 units in its length according to what is given as the question. And it is equals to DC. DC is the missing side, so it is. Plus AB. AB equals to 50 units in its length according to what is given in the question. So in total, if you found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82. So 82 equals to DC plus 50. Here we'll subtract 50 from this equation, and you get that the missing side DC is equal to 82 minus 50 is 32. This equals to 32 units in its length. So actually, this is the missing side DC. This equals to 32 units in its length. In the next step, we will do a construction, that is to say, from this point C, we will do perpendicular on AB. Again, from point C, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. Likewise, we will do another construction, that is to say, from this point D, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. So we have those two angles. They are both defined as one-sided interior angles, and they are located between the parallel lines DC and AB. Why DC is parallel to AB? Because of the fact that ABCD is a trapezoid. In trapezoid ABCD, we have one pair of parallel sides. The one pair of parallel sides are DC is parallel to AB. So those two one-sided interior angles are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. So, okay, click on Rule 17. According to Rule 17, the sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B. Line C, the red line C, cuts those two parallel lines at those 2 points. Those two angles, alpha and beta, they are both defined as one-sided interior angles. Those two one-sided interior angles are located between the parallel lines A and B, and therefore, according to this rule, Rule 17, the sum of those two one-sided interior angles is equal to 180 degrees. That is why alpha plus beta equals to 180 degrees. So we can actually implement Rule 17 in our drawing, because in our drawing we have those two one-sided interior angles are located between the parallel lines CB, CD and AB, and therefore the sum of those two one-sided interior angles must be equal to 180 degrees according to Rule 17. This angle is a right angle, that is to say it is equal to 90 degrees in its size, plus this missing angle, that is actually angle DCJ. In total, the sum of those two one-sided interior angles that are located between the parallel lines CD and AB must be equal to 180 degrees according to Rule 17. So 90 degrees plus the missing angle DCJ must be equal to 180 degrees according to Rule 17. So here we subtract 90 degrees from the equation and get the side of the missing angle DCJ. The size of the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. This is angle DCJ. This is equal to 90 degrees in its side according to Rule 17. Likewise, those two angles, they are both defined as one-sided interior angles and are located between the same parallel lines DC and AB, and therefore, according to Rule 17, the sum of those two one-sided interior angles must be equal to 180 degrees. This angle is a right angle, that is to say it is equal to 90 degrees in its size, plus the missing angle, the angle CDN. In total, the sum of those two one-sided integrals must be equal to unrelated integrals according to rule 17. Here we subtract 90 degrees from this equation and we get that the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So the missing angle CDN is equal to 90 degrees in its size. This is the missing angle CDN, that is equal to 90 degrees in its size according to rule 17. So in total, we should find out that in quadrilateral CD and J, inside this quadrilateral CD and J, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So relate to quadrilateral PCJN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the same rule, in the same rectangle DCJN, side DN must be equal to the opposite side CJ. So dN equals to Cj. In the next step, we'll focus on those two right triangles. On those two right triangles, this is the right triangle DNA, and this is the right triangle CJB. On those two right triangles, those two sides are equal to each other. Those two sides, each of them is equal to 41 units and therefore they are also equal to each other. Those two sides are also equal to each other. I will prove that those two sides are equal to each other. So I copied those two right triangles in a new page and I prove that those two sides are also equal to each other. They are equal to each other according to the Pythagoras theorem. If we implement on those two right triangles the Pythagoras theorem, we find out that those two sides are equal to each other. That is to say, AN equals to JB. So actually, those are the two right triangles that are coming from the original drawing. The hypotenuse DA equals to 41 units in its length. It is equals to CB, that is also equals to 41 units in its length. So I define those two sides as Y. You can also define them as 41, that each of them is equal to 41, but anyway, you define those two sides, the length of those two hypotenuses as Y. Those two sides are also equal to each other, so I define those two sides, each of them as X. So while those two sides AN is equal to JB. According to the Pythagoras theorem, this right triangle DNA, y square equals to x square plus an square. Y square equals to x square plus an square. Here, I subtracted x square from this equation and finally found out that an square equals to y square minus x square. Here I took a root out of this equation and finally found out that the length of the missing side an is equal to the square root of y square minus x square. Likewise, I repeated on the same process in this right triangle. I actually implemented the Pythagoras theorem on this right triangle CJB. This right triangle, according to the Pythagoras theorem, y square equals to x square plus jb square. Y square equals to x square plus jb square. Here I subtracted x square from this equation and I found out that jb square equals to y square minus x square. Here I took a root out of this equation and finally found out that the missing side JB equals to the square root of y squared minus x squared. So both those two sides are equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, AN equals to JB. So in total, we found out that all the three sides of this right triangle DNA are correspondingly equal to all the three sides of this right triangle CJB, and therefore those two right triangles can go into each other according to side rule. Okay, again, those two sides are both equal to y, therefore they are equal to each other. Those two sides are both equal to x, and therefore they are equal to each other. And I want to prove that AN equals to JB. Therefore, those two triangles can go into each other according to side rule. So that is done. If we found out that the right triangle DNA congruent. This is the sign of congruent to the right triangle CJB. This right triangle CJB according to side rule. Actually, we already found out that AN equals to JB. Yeah. AN equals to JB. So we can write down that AN equals to JB. So if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. The length of side AB equals to 50 units from one side. But for the other side, AB also equals to x plus 32. And again, from one side, AB equals to 50 units. From the other side, AB also equals to x plus 32. AB actually consists of 3 line segments. The first one is x, the second one is also x, and the third line segment is equals to 42 in its units in its length. X plus x is 2x, so in total 50 equals to 2x plus 32. Here we subtract 32 from this equation. Finally we get that 50 minus 32 is 18, equals to 2x. Here we divide this equation by 2, and finally we get that the missing side x equals to 18 over 2 is 9. Now here JB is equals to x is equal to 9 units in its length. In the next step, I'll copy the right triangle CJB in a new page and we will implement the Pythagoras theorem on this right triangle CJB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. the hypotenuse CB equals to 41 units in itself, and JB equals to 9 units in itself. CJ is the missing side, so we find out the length of CJ by implementing the Pythagoras theorem, and this right triangle CJB. Here by PT is the abbreviation from Pythagoras theorem. So actually, this is the right triangle CJB that I got from the original drawing. In this right triangle CJB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. So I'll write it down. CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681, and this is equals to CJ squared. CJ is the missing side, so we inherit it, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. Here is some time 81 from this equation. And when you get that 1681 minus 81 is 1600 equals to CJ squared. CJ squared equals to 1600. Here we'll take out all of this equation. And when you get that the missing side CJ is equal to the square root of 1600, that is 40. So CJ equals to 40 units in its length. This is the missing side CJ equals to 40 units in its length. Our task is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. So the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases are DC and AB. So it is DC plus AB times the height over 2. The height is CJ. Why the height is CJ? Because it rates 90 degrees with the two parallel bases. So times the height CJ over 2. And again, if you want to know that the area of this trapezoid ABCD, that is the area that we are looking for in this question, it is equal to the sum of its two parallel bases, roughly DC plus AB, times the height CJ over 2. DC is 32 plus AB is 50 times CJ is 40 over 2. So in total we found out that the area of trapezoid ABCD is equal to 32 plus 50 times 40 over 2. 32 plus 50 is 82. And 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20. 82 times 20, 82 times 20 is 1640 square units. And that is the answer to the question. And again, we found out that the area that we are looking for in this question, that is the area of this trapezoid ABCD, is equal to 1640 square units in its size. So we finish with the first question. In the next step, I will present to the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is side AB, that equals to 10 units in its left. This is side DC, that equals to 25 units in its left. This is angle ABC, that is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that equals to 45 degrees in its size. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we will do a construction, that is to say, from this point B, we will draw perpendicular on DC. Okay, again, from point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point N. In the next step, we will do another construction, that is to say, from point A, this point A, we will draw perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and BN. This point is point M. By doing those constructions, we actually created the quadrilateral AEM and D. Inside quadrilateral AEM and D, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this surface again, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this surface again must be equal to 90 degrees in its size. So in quadrilateral A, M, and D we have 4 angles. Therefore, according to rule 5, quadrilateral AM and D is a right angle. So let you know, this is quadrilateral AM and D, that is a right angle according to rule 5, because it has 4 right angles. We define the length of side AM as A. We know that the opposite sides of a rectangle are equal to each other. So rectangle AM and D, side AM must be equal to the opposite side ND, but AM is A, therefore the opposite side ND must be also equal to OA units in its length. In the next step, we will focus on this right triangle, triangle B and C. On the right triangle B and C, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this pelvis angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We will continue to focus on this right triangle B and C. We have the rule that says that in front of equal angles in a triangle, they are equal sides. Again, we have the rule that says that in front of equal angles in the triangle, they are equal sides. So in this triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other, according to the rule that I mentioned. What is the length of NC? NC equals to DC minus DN. Again, sorry, moving on. NC equals to DC minus ND. DC minus DN. NC equals to DC minus DN. So NC in total equals to DC is 25 minus DN is A. So in total NC equals to 25 minus A units in its length. So in the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other. But side NC is 25 minus A, therefore NBN must be also equal to 25 minus A units in its length. Okay, this is side BN. This is equals to 25 minus A units in its length. This is the big angle ABC is the right angle, it is equal to 90 degrees in its size. So the big angle ABC minus the small angle NBC, that is 45 degrees, must be equal to the missing angle ABM. Therefore the missing angle ABM must be equal to angle ABC, that is 90 degrees, minus this angle NBC, this is 45 degrees. 90 degrees minus 45 degrees is 45 degrees. So angle ABM must be equal to 45 degrees in its size. We focus on the right small triangle ABM. The right small triangle ABM, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other with their lengths. But side AM is A, therefore side BM must be also equal to A units in its length. What is the length of side AM or line segment M? Side MN or line segment MN? MN equals to BN minus BM. So as you know, MN equals to BN minus BM. MN equals to BN minus BM. So Mn in total equals to Bn is 25 minus A minus BM. BM is A. So in total, MN equals to 25 minus A minus A. That is 25 minus 2A. MN equals to 25 minus 2A units in its there. This is side MN, that is equals to 25 minus 2 units in its length. In rectangle AM and D, the opposite sides are equal to each other. That is to say, side MN must be equal to the opposite side AD. But MN is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2 units in its length. So I said no. If we found out that this is the missing side AD, this is also equals to 25 minus 2A units in its length. In the next step, we'll implement the Pythagoras theorem on this right small triangle ABM. So copy the right small triangle ABM in an equation. We will implement on it the Pythagoras theorem. Here by PT is the proportion for Pythagoras theorem. Actually, this is the small right triangle ABM, this is the common small dimensional domain. This small right triangle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. So I write it down. BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, that is 100. And it is equal to BM squared. BM is 8, therefore BM squared is 8 squared plus AM squared. AM is also 8, therefore AM squared is 8 squared. So in total, 100 equals to A squared plus A squared, that is 2A squared. So if you found out that 100 or 2A squared equals to 100. This is quadrilateral A, B, and D. Quadrilateral A, B, and D is a trapezoid. Why quadrilateral A, B, and D is a trapezoid? Because we know that the opposite sides of a rectangle are parallel to each other. So in rectangle AM and D, side MN is parallel to the opposite side AD. But MN is part of the third line BN. Why BN is the third line? Because of the fact that this is angle BMN is equal to 180 degrees. And we know that any angle that is equal to 180 degrees in its sides, it is defined as a straight line. So BN is a straight line, and Mn is part of the third line Bn. Again, Mn is part of the third line Bn. And if a part of the third line is parallel to another third line, then the third line itself must be also parallel to the other third line. That is to say, Bn is parallel to AD. So in quadrilateral A, B, and D, side Bn is parallel to the opposite side AD. And this is exactly the definition of a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. In trapezoid A, B, and D, side Bn is parallel to side AD, and therefore quadrilateral A, B, and D is a trapezoid. So I know if you found out that this is quadrilateral A, B, and D, that is a trapezoid. What is the area of this trapezoid? Trapezoid A, B, and D. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel sides times the height over 2. I already proved that side Vn is parallel to side AD. So the sum of its two parallel sides is Vn plus AD. Times the height AM over 2. Why AM is the height? Because the AM carries an interface with the two parallel bases. So it is the height AM over 2. So in total we should find out that the area of this trapezoid A, B, and D is equal to the sum of its two parallel bases, that is actually Bn plus AD, times the height AM over 2. Bn is 25 minus A plus AD. AD is 25 minus 2A times the height AM. AM is A divided by 2. So in total we should find out that the area of this trapezoid A, B, and D is equal to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50, and A minus 2A is minus 3A. So in total the numerator we have 50 minus 3A times A divided by 2. Here we open the brackets of this expression in the numerator, and we get that 50 times A is 50A, minus 3A times A is minus 3A squared, divided by 2. So in total we should find out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2. So as you know, we should find out that the area of this trapezoid A, B, and D is equal to 50A minus 3A squared over 2. And again, if you found out that the area of trapezoid A, B, and D is equal to 50A minus 3A squared over 2. our task is to find out the area of this quadrilateral, quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of quadrilateral ABC in total equals to the area of trapezoid A, B, and D plus the area of this right triangle B and C. So it is done. We have found out that the area of this quadrilateral ABCD equals to the area of this trapezoid A, B, and D. Plus the area of this right triangle B and C. And again, if we found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, in total it is equal to the area of trapezoid A, B, and D plus the area of the right triangle B and C. We already found out that the area of this trapezoid A, B, and D is equal to 50A minus 3A squared over 2 plus the area of this right triangle B and C. The area of the right triangle B and C equals to the base NC times the height NB over 2. And again, we already found out that the area of trapezoid A, B, and D is equals to 50A minus 3A squared over 2, and the area of the right triangle B and C equals to the base NC times the height NB over 2. So the area of quadrilateral ABCD is equal to 50A minus 3A squared over 2. That is the area of trapezoid A, B, and D plus the area of this right triangle B and C. This is equals to NC. NC is 25 minus A times NB. NB is also 25 minus A, so it is 25 minus A squared divided by 2. So in total, we should find out that the area of this quadrilateral ABCD equals to 50A minus 3A squared over 2 plus 25 minus A squared over 2. Here we open the brackets of this expression and get that in total the area of quadrilateral ABCD equals to 50A minus 3A squared over 2 plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625. Minus 2 times 25 times A is minus 58 plus A squared. 58 minus 58 is 0, so those expressions get cancelled. And you're left only with 625 minus 3A squared plus A squared is minus 2A squared over 2. So in total, we found out that the area of quadrilateral ABCD equals to 625 minus 2A squared over 2. But we already found out that 2A squared equals to 100. We can substitute 2A squared in this equation by 100. We do it now, we get that the area of quadrilateral ABCD in total equals to 625 minus 2A squared. 2A squared is 100 over 2. 625 minus 100 is 525 divided by 2. 525 over 2 is 262.5 square units. That is the answer to the question. I repeat again, I have found out that the area that we're looking for this question, that is the area of this quadrilateral ABCD. In total it is equals to 262.5 square units in its size. So finish with the first method. In the next step I present to you how to find out the area of this quadrilateral ABCD by using a second method. In the second method, we will do a construction. That is to say, we'll extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is their touching point. So we'll define the touching point of the extended side DA with the extended side CB. This point is point M. By doing those constructions, we're going to do the right big triangle MDC. In the right big triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this vertex angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We will continue to focus on the big right triangle MDC. On the big right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But DC is 25, therefore MD must be also equal to 25 units in its length. So side MD equals to 25 units in its length. MC, side MC is the hypotenuse of the right triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if we focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of MC at point B? We have this angle that is right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle MBA, this is the small right triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this vertex angle must be also equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We continue to focus on the small right triangle MBA. The small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AB is 10, therefore side MB must be also equal to 10 units in its length. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD must be equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. So write it down. The area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. Again, if we found out that the area that we were looking for in this question, that is the area of quadrilateral ABCD, in total this is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height DM over 2. And again, this big right triangle MDC in total is equal to the base DC times the height DM over 2. Minus the area of the small right triangle MDA. The area of the small right triangle MDA equals to the base AB times the height BM over 2. And again, the area of this small right triangle MBA equals to the base AB times the height BM over 2. DC is 25 times DM is also 25 minus AB is 10 and BM is also 10. So in total we found out that the area of quadrilateral ABCD in total is equal to 25 times 25 minus 10 times 10. 25 times 25 is 625 minus 10 times 10 is 100 divided by 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So actually, in both methods, we found out that the area of this quadrilateral ABCD is equal to 262.5 square units in its size. So we finish with the second question. In the next step, I'm sorry, the lecture, we'll start with the first question, of course. Our task in the first question is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. I repeat again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD, and because of the fact that side DC is parallel to side AB, this quadrilateral ABCD is defined as a trapezoid. And if we define the length of the two parallel sides are defined as the bases of the trapezoid. So DC and AB are the bases of trapezoid ABCD. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is to say A plus B, times the height H over 2. The height H must create 90 degrees with the two parallel bases. Repeat again, this trapezoid ABCD equals to the sum of its two parallel bases, that is actually A plus B, times the height H over 2. So first of all, we define the relevant points to the question with letters. We define the point of tendency of tangent DC with this circle. This point is point E. Likewise, we define the point of tendency of tangent DA with this circle. This point is point G. We define the point of tendency of tangent CV with this circle. This point is point F. And we define the point of tendency of tangent AB with this circle. This point is point H. In the next step, We implemented rule 2 in our domain. And click on rule 2, according to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So, in the domain we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our domain. If we focus on this common standpoint, point D, from this common standpoint, point D, we have two tangents to this circle, tangent DE and tangent DG. And according to rule 2, they are equal to each other. This is to say D equals to DG. So if we define the area of tangent DE as A, then the area of tangent DG must be also equal to A because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint, point C. From this common standpoint, point C, we have two tangents to this circle, tangent CE and tangent CF. And according to rule 2, they are equal to each other. That is to say, CE equals to CF. So if we define the area of tangent CE as C, then the area of tangent CF must be also equal to C because they are equal to each other according to rule 2. Likewise, we focus on this common standpoint, point A. From this common standpoint, point A, we have two tangents to this circle, tangent AH and tangent AG. And according to rule 2, they are equal to each other. That is to say, AH equals to AG. So if we define the area of tangent AG as B, then the area of tangent AH must be also equal to B because they are equal to each other. And finally, we focus on this common standpoint, point B. From this common standpoint, point B, we have two tangents to this circle, tangent BH and tangent BF. And according to rule 2, they are equal to each other. That is to say, BH equals to BF. So if we define the area of tangent BH as D, then the area of tangent BF must be also equal to D because they are equal to each other according to rule 2. So what is the area of side DA plus side C plus the opposite side CB? From the domain, it is very easy to say that CA plus DA, side DA, plus CA in total equals to A plus B plus C plus D. And again, in trapezoid ABCD, side DA plus the opposite side CB in total equals to A plus B plus C plus D. Likewise, what is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you now know that DC plus AB also equals to A plus B plus C plus D, and because of the fact that those two expressions are both equal to A plus B plus C plus D, it means that they are equal to each other. That is to say, DA plus CB equals to DC plus AB. DA is 41 plus CB is also 41. DC is the missing side plus AB is 50. 41 plus 41 is 82 equals to DC plus 50. Here we subtract 50 on this equation. If I found out that 82 minus 50 is 32. So if we found out that the missing side DC is equal to 32 units in its length. In the next step, we did the construction. That is to say, from this point C, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Again, from point C, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. Likewise, from this point D, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. We know that ABCD is a trapezoid. In trapezoid ABCD, we have one pair of parallel sides. The two parallel sides are DC and AB. So DC is parallel to AB in trapezoid ABCD. Here, those two angles are both defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, according to rule 17, the sum of those two one-sided interrogants is equal to 180 degrees. So this angle is right angle plus this missing angle, that is angle DCJ, in total must be equal to 180 degrees according to rule 17. So again, according to rule 17, 90 degrees plus the missing angle DCJ is equal to 180 degrees. Here we subtract 90 degrees from this equation and find out that the missing angle DCJ equals to 180 degrees plus 90 degrees is 90 degrees. So actually, this is the missing angle DCJ, this is equal to 90 degrees in its size. Likewise, those two angles are also defined as one-sided interangles, and they are located between the parallels DC and AEB. And therefore, the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. So this is a right angle plus the missing angle CDN, in total it must be equal to 180 degrees according to rule 17. So if we found out that 90 degrees plus the missing angle CDN, in total it must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation, if I found out that the missing angle CDN equals to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle CDN that is equal to 90 degrees in its size. So if we found out that in quadrilateral DCJN we have 4 right angles. Therefore, quadrilateral DCJN is right angle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side JN must be also equal to 32 units in its length. Likewise, according to the sum rule, in the sum rectangle DCJN, side DN must be equal to the opposite side CJ. So those two sides must be equal to each other. In the next step, according to the rule, the opposite sides of a rectangle are equal to each other. In the next step, we focus on those two right angles, right angle DNA and this right angle CJB. On those two right angles, those two sides are equal to each other. Those two sides are also equal to each other. Each of them is equal to 41, therefore they are equal to each other. Those two missing sides are also equal to each other. If we prove that those two sides are equal to each other, if we copied those two right angles in an equation, I prove that those two sides are equal to each other. So actually, those are the two right angles that are coming from the original domain. The hypotenuse DA equals to 41, and it is equals to the hypotenuse CB, it is also 41. So instead of 41, I define the length of the two hypotenuses as y. We already found out that dn equals to cj, according to the rule that the opposite sides of a rectangle are equal to each other. So if the length of dn is x, then the length of cj must be also equal to x. Now we have to prove that side AN is equal to side JB. Actually implemented the Pythagoras theorem on this right angle DNA. The right angle DNA, according to the Pythagoras theorem, y squared equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. So here we subtracted x squared from this equation, and I found out that an squared equals to y squared minus x squared. Here we to hold all of this equation, I found out that the missing side an in totality is equals to the square root of y squared minus x squared. Repeated on the same process here. In the right angle CJB. In the right angle CJB, according to the Pythagoras theorem, y squared equals to x squared plus jb squared. Here we subtracted x squared from this equation, I found out that the jb squared equals to y squared minus x squared. Here we took out of this equation, I found out that the missing side jb equals to the square root of y squared minus x squared. So those two sides, they are both equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, side an equals to side jb. So today we found out that those two sides are both equal to x, therefore they are equal to each other. Those two sides are both equal to y, therefore they are equal to each other. And finally found out that side an equals to side jn. So if we found out that all the three sides of this right angle DNA corresponding equal to all the three sides of this right angle CJB, and therefore those two right angles can go into each other according to side rule. we found out that the right triangle DNA is congruent. This is the sign of congruent to the right triangle CJB according to side rule. And we already found out that side AN actually proved that side AN equals to side JB. So if you define side AN as x, then side JB must also equal to x because they are equal to each other. This is side AB. This equals to 50 units in its length, according to what is given in the question from one side, but from the other side, side AB also equals to x plus 32. Okay, again, from one side, side AB equals to 50, according to what is given in the question, but from the other side, side AB also equals to x plus 32. So from this equation, we get that 50 equals to 2x plus 32. 50 equals to 2x plus 32. Here, subtract 32 from this equation, and I found out that 50 minus 32 is 18, so 18 equals to 2x. Here, we divided this equation by 2, and I found out that x equals to 18 over 2, this is 9. Okay, this is side JB equals to x, and x equals to 9, so JB equals to 9. CB equals to 41, and CJ is the missing side, so I copied this right triangle CJB in an page and implemented the particular theorem on this right triangle CJB. So actually, this is the right triangle CJB that I copied from the original drawing. In this right triangle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 681, and it is equals to CJ squared. CJ is the missing side, so we have to see this, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we have found out that 1681 equals to CJ squared plus 81. Here, we subtracted 81 from this equation, and I found out that 681 minus 81 is 6. 1681 minus 81 is 1600, so 1600 equals to CJ squared. Here we took out all of this equation, and I found out that CJ equals to the square root of 1600, that is 40. So this is sign CJ equals to 40 units in its length. This is the missing sign CJ, that equals to 40 units in its length. CJ actually, it is the height of this trapezoid ABCD. Our test is to find out the area of this trapezoid ABCD. According to the formula that I presented to you, the infinite trapezoid equals to the sum of its two parallel bases times the height over 2. The two parallel bases of this trapezoid ABCD are DC and AB, so it is DC plus AB times the height JB or times the height CJ over 2. So in total, we found out that the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height CJ over 2. DC is 32, AB is 50, and CJ is 40. Divided by 2. 32 plus 50 is 82, and 40 over 2 is 20. So in total, the area of trapezoid ABCD equals to 82 times 20, that is 1640 square units in size. So if you found out that the area of this trapezoid ABCD is equal to 1640 square units in size. So I finish with the first question. In the next step, I presented you the second question, and solve the second question by using two different methods. Our task in the second question is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. Side AB equals to 10 units in its length, side AC equals to 25 units in its length. This is angle ABC, that is right angle. This is angle ADC, that is also right angle. This is angle BCD, that is equals to 45 degrees in its size. Again, our test is to find out the area of this trapezoid ABCD. The area of this quadrilateral ABCD. So, first of all, we did the construction, that is to say from point B, we do perpendicular on DC. Again, from point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point B and DC. This point is point M. In the next step, we did another construction, that is to say from point A, we do perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and B, and this point is point M. By doing this construction, we're going to do quadrilateral AM and D. In quadrilateral AM and D, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, it must be equal to 360 degrees according to the rule, and the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this piece again must be equal to 90 degrees in size. So quadrilateral AM and D is 4 angles, and therefore it is a rectangle. We define the length of side AM as A. So in rectangle AM and D, the opposite sides are equal to each other. That is to say, side AM equals to the opposite side DN. But AM is A, therefore the opposite side DN must be also equal to A units in its length. In the next step, we focus on this right angle B and C. In the right angle B and C, this angle equals to 90 degrees. This angle equals to 45 degrees, and therefore this value angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We have the rule that in front of equal angles in the triangle, they are equal size. So in the right angle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But NC is 25 from A, because it is DC, it is 25 from the end that is A, so it is 25 from A. Therefore, BN must be also equal to 25 from A units in itself, according to the rules that I mentioned. In the next step, we focus on this big right angle ABC is equals to 90 degrees in size. So, angle ABC minus this small angle NBC, in total must be equal to the missing angle ABM. So the missing angle ABM equals to angle ABC, this is 90 degrees, minus this angle NBC, this is 45 degrees. 90 degrees minus 45 degrees is 45 degrees. So this is the missing angle ABM, this is equals to 45 degrees in size. So in the small right angle AMB, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So we continue to focus on this small right angle MBA. The small right angle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AM is A, therefore side BM must be also equal to A units in its length. What is the length of MN? MN equals to BN minus BM. Again, MN equals to BN minus BM. So MN equals to BN is 25 from A minus BM, that is A. So in total, MN equals to 25 from A minus A, that is 25 minus 2A. So MN equals to 25 minus 2A units in its length. So in the left angle AM and D, the opposite sides are equal to each other. That is to say, side MN equals to the opposite side AD. But MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. In the next step, we implemented the Pythagoras theorem on this right angle ABM. So I copied the right angle ABM in an equation, we implemented the Pythagoras theorem on this right angle ABM. So this is the right angle ABM that I got from the drawing. This right angle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, this is 100, and it is equals to BM squared. BM is 8, therefore BM squared is A squared, plus MA squared. MA is 8, therefore MA squared is A squared. So in total, 100 equals to 8 squared plus 8 squared is 2A squared. So if we found out that 2A squared equals to 100. This is quadrilateral AB and D. Quadrilateral AB and D is a trapezoid. Why quadrilateral AB and D is a trapezoid? First of all, we know that the opposite sides of a rectangle are parallel to each other. So in rectangle AM and D, side MN is parallel to the opposite side AD. BN is a straight line because this is angle BMN is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, BN is a straight line. But BN is part of the but MN is part of the third line BN and is parallel to AD. If a part of a third line is parallel to another third line, then the third line itself BN must be also parallel to AD. So in quadrilateral AB and D, side BN is parallel to the opposite side AD, therefore quadrilateral AB and D is a trapezoid. And again, if you found out that quadrilateral AB and D is a trapezoid because it has one pair of parallel sides. What is the area of this trapezoid AB and D? The area of trapezoid AB and D must be equal to the sum of its two parallel sides, that is to say BN plus AD times the height AEM over 2. The area of trapezoid AB and D in total equals to the sum of its two parallel sides, that is to say BN plus AD times the height AEM over 2. BN is 25 minus A plus AD is 25 minus 2A divided, multiplied by AM. AM is 8 divided by 2. So again, BN is 25 minus A plus AD is 25 minus 2A times AM, that is 8 divided by 2. 25 plus 25 is 50, and minus 8 minus 2A is minus 3A times 8 over 2. So in total, we found out that the area of trapezoid AB and D equals to 50 minus 3A times A over 2. Here we open the brackets and found out that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, we found out that the area of this trapezoid AB and D is equal to 58 minus 3A squared over 2. Okay, again, the area of this trapezoid AB and D in total is equal to 58 minus 3A squared over 2. Our test is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the domain it is very easy to see that the area of this quadrilateral ABCD equals to the area of trapezoid AB and D plus the area of this right triangle B and C. Again, the area of this quadrilateral ABCD, that is the area that we are looking for in this question. In total, it is equals to the area of trapezoid AB and D plus the area of the right triangle B and C. We already found out that the area of trapezoid AB and D is equals to 58 minus 3A squared over 2 plus the area of the right triangle B and C. The area of the right triangle B and C equals to the base NC times the height NB over 2. Because again, the area of the right triangle B and C equals to the base NC times the height NB over 2. So the area of quadrilateral ABCD equals to 58 minus 3A squared over 2 plus NC is 25 minus 8 times NB. NB is also 25 minus 8, so we have 25 minus 8 squared divided by 2. So in total, we found out that the area of trapezoid AB and D equals to 58 minus 3A squared over 2 plus 25 minus 8 squared over 2. So it is 58 minus 3A squared over 2. Open the brackets and here we found out that 25 squared is 625 plus 8 squared minus 2 times 25 times 8, that is minus 58 plus 8 squared divided by 2. 58 minus 58 is 0, so those two expressions get cancelled. And we have plus 3A squared plus 8 squared is minus 2A squared plus 625. So in total, we found out that 625 minus 2A squared over 2 is the area of quadrilateral ABCD. But we already found out that 2A squared equals 200. So we can substitute 2A squared here by 100. We did it, and we found out that the area of quadrilateral ABCD in total equals to 622 minus 2A squared is minus 100 divided by 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. So if you found out that the area of this quadrilateral ABCD in total it is equal to 262.5 square units in size. We finish the first method, and the next step I presented you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we did the construction. That is to say, we extended side DA and side CB of this polygonal ABCD by a straight line until they touch each other. This is the touching point. We define the touching point of the extended side DA with the extended side CB. This point is point M. When doing this construction, we added the right big triangle MDC. The right big triangle MDC, this angle equals to 9 degrees, this angle equals to 45 degrees, and therefore this vertex angle must be equal to 45 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other and the reverse. But side DC is 25, therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the right big triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the angles on one side of a straight line is equal to 180 degrees. So in case we have the left side of MC at point B, we have this angle, that is right angle, plus this missing angle. In total, the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this vertex angle must be equal to 45 degrees in its size according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. So in the small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AB is 10, therefore the side MB must be also equal to 10 units in its length. Our test is to find out the area of this polygonal ABCD. So what is the area of polygonal ABCD? From the drawing, it is very easy to see that the area of polygonal ABCD equals to the area of the big right triangle MDC minus the area of this one right triangle MBA. The area of polygonal ABCD in total is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height DM over 2. So again, the area of the right triangle MDC equals to the base DC times the height DM over 2. Minus the area of this small right triangle MBA. What is the area of the small right triangle MBA? It is equal to the base AB times the height BM over 2. So again, the area of the right triangle MBA is equal to the base AB times the height BM over 2. DC is 25. MD is also 25. So the area of the big right triangle DMC is 25 times 25 over 2 minus AB is 10 and BM is also 10. So the area of the small right triangle MBA is equal to 10 times 10 over 2. 25 times 25 is 625 minus 10 times 10 is 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in size. So showing both methods, you should find out that the area of this polygonal ABCD is equal to 262.5 square units in size. Okay, thank you very much.